Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today I really just want to wrap up the work we've been doing with computing the matrix rank and solving systems of linear equations. And I did mention when we did that original episode, I think that was 3 episodes ago now in this series, that we looked at solving systems of linear equations. And I said there were ways that we could still determine something interesting and useful even when we have a system of equations that has no unique solution. And that's actually what we're going to look at today. So today we're going to look at how we can use the matrix rank that we've been working on for the last 2 episodes to tell us which of the 2 possible categories an unsolvable system of equations falls into. That is, whether it has no unique solution or whether it has no solutions at all. But information that could in some circumstances still be useful even when you have a system that can't be solved. Anyway, I don't want to do a long introduction, but quickly, just before we dive into actually looking at the code and how I've gone about doing that, I just want to say that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try and make a video roughly once a week, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, without much further ado, let's jump to it and let's have a look how we can use the matrix rank to determine which of the 2 categories any unsolvable system of equations might fall into. Okay, so just really wrapping up our work looking at matrix rank and solving systems of linear equations. As I've just said in the introduction, what we want to look at here is how we can go about using the rank that we've been talking about in the last 2 videos to tell us something about the system of equations that we're trying to solve in the event that we have a system that is unsolvable. I just very quickly want to recap on what we talked about to do with solving systems of linear equations. So we talked about doing this using the Gaussian elimination method, and we talked about how this is a better way of solving a system of linear equations compared to computing the matrix inverse and multiplying through by that. Simply, it's mostly because it's more efficient. We also The objective of Gaussian elimination is to transform the matrix A into row echelon form. I don't want to talk about that too much now. This is an example of a matrix in row echelon form. So we have all the 0 numbers down here in the lower left, and then all the non-zero numbers in the top right corner. And technically all the leading numbers for each row should be 1. Actually, for solving a system of linear equations, we don't need to insist upon that, but that's something else. So that's just about that, and that is an example of the row echelon form. And we transform our matrix into that using the elementary row operations. We talked about all of that in the previous video, and then we introduce this very simple example. Now this I just want to pay a little bit of attention to. So in matrix form, our system of equations looks like this. We have a matrix of coefficients here, and then we have our variables x, y, and z, and then we have the other coefficients here. So this is a times x equals b, classic arrangement. And in order to apply Gaussian elimination to that, we would augment the far left-hand part in blue with the right-hand part shown here in yellow. So we would get a matrix here consisting of 3 rows of 4 columns. And then we would work on that using the elementary row operations. And if we do that for this particular example, we get a result that looks like this, which we can then separate back out, and then we can use that information to work through, and we can solve x, y, and z. And we've looked at all of that before, and we've looked at how we can write code to implement an algorithm to do that process. So if you haven't seen those videos, I strongly suggest go back and have a look at those. Okay, but there are 3 possible situations for any system of equations. The first is that the system has a unique solution, i.e. we can solve it. The second is that the system has an infinite number of solutions, or mathematically, in mathematical terms, no unique solution. And the third is that the system has no solutions at all. So the second and the third items there are situations where we simply cannot solve the system of equations. The first is really the only situation where it's possible to actually find a solution. So our challenge is to determine which of these any given system of equations falls into, so that we can say something a little bit more about it in the event that we can't find a solution. Okay, so I showed in the previous videos these visual examples, and this is for a 3-dimensional system, so a system of 3 equations and 3 unknowns, and we can plot those geometrically. So this is what a system would look like if there is a unique solution. We can plot each equation as a plane in three-dimensional space, and then we find the point where all three of those planes intersect, just here, which happens to be at x equals 4, y equals 1, z equals -6, and that is the solution to the system of equations. So we can represent that geometrically if we're dealing with three-dimensional systems. An example of a system which has no unique solution, so it has an infinite number of solutions, would be something like this, where all of the planes intersect along a single line. And an example, a really obvious example of a system that would have no solution at all, would be something like this, where we have three parallel planes. So obviously these never intersect at all, so very clearly that system would have no solutions. We can use the matrix rank to determine which category any given system of equation falls into. Okay, so there are two matrices that we need to consider for this, not just one. If we go back to thinking about our system of equations, which we represent like this, we have the coefficient matrix A11 through to A33, x, y, z are variables, and then we also have B1, B2, and B3 over here. We actually have two matrices now that we want to consider. The first is the original coefficient matrix A, just A11 through to A33, and then the second is the augmented coefficient matrix, which we're going to call AB, which has the terms A11 through to A33 and also the terms B1, B2 and B3 augmented there. So we have one 3x3 matrix and one 3x4 matrix. For reasons that I think will become clear in a moment, it's important to consider both of those. Okay, so we can compute the rank of A and the rank of AB, and we can compare the results with the number of rows n. And if we do that, we find that there are three possible conditions. The first is that the rank of A is equal to the rank of AB is equal to n, the number of rows. The second is that the rank of A is equal to the rank of AB, and they are both less than n, the number of rows. And the third is that the rank of A is less than the rank of AB. Remember, AB is the augmented matrix and A is the original coefficient matrix. And those imply the situations as follows. If the rank of A is equal to the rank of AB is equal to the number of rows, that means that there must be a unique solution to that system of equations. If the rank of A is equal to the rank of AB, and they are both less than n, the number of rows, that implies there is no unique solution, or there's an infinite number of solutions. And the third one, of course, if the rank of A is less than the rank of AB, the augmented matrix, then that simply implies that no solutions exist at all. Okay, so we can see what we need to do just to finish this off really is to write code to calculate the rank of the original coefficient matrix, the rank of the augmented coefficient matrix, and then compare those two with each other and with the number of rows, and then we should be able to determine something about our system of equations, even in situations where there is no unique solution. Okay, so here we're looking at the qblinssolve.h code. We talked about this quite extensively in the episode on solving systems of linear equations, so I don't want to go through the whole process again, but I have made some fairly substantial changes to this code since we talked about that initially. And so what I'd like to do is just talk about those. The first thing that you'll notice is that I've defined these two error codes now using const expression, as integers. We have qblinssolve underscore no unique solution, which I've set equal to -1. And qblinssolve underscore no solutions, which is equal to -2. Now the reason I've done that, and the reason I've made changes to this function, is that I wanted this function to be able to return error codes when it's given a system of equations that it cannot solve. So previously, if you gave it a system with no solution, it would simply return a nonsensical response. But there might be no way of detecting that that response didn't make any sense, and that could be, dangerous for other code further down the line. So what I've done is modify qblinssolve so it now returns an integer, and in fact it's going to return one of these two values, or 0, depending on whether it was able to solve the system or not. And in order to do that, we're no longer returning the result as a QB vector object here. So what I've done is added an additional reference here, QB vector type T, reference result vec. And I've also changed these to be passed by reference, as previously I had specified these as pointers. Pointers is kind of a C thing, and it's not really necessary to use pointers in C++, unless, of course, you need to allow for the possibility of a pointer being null. A reference can never be null, so that is the difference. And there might still be cases where you have to allow for a null condition, and then you would use pointers. But for what we're doing here, simply pass by reference does the job entirely. So we pass result vec by reference, and then we can still modify that, put the output that we want into it, and that will work as we expect. In order to support that, I had to make a change to the QB vector class as well, but we'll come back to that later. Okay, so other than that, only minor changes in the code simply to support the change away from vectors to support changing from pointers to pass by reference. So we no longer need to use the dereference operator for things like this and so on, but that's all fairly obvious. Okay, and we use the dot operator rather than the minus greater than symbol to access the member functions and member elements of those classes. So everything here is the same. Now the only thing that has changed is we bring in here these two new lines here. Original matrix equals input matrix dot rank. So we talked in the previous video and the previous but one video about computing the matrix rank, so you can go and have a look at those if you haven't seen them. And that gives us the rank of our original coefficient matrix, which we've called the A matrix. And then down here, after we've joined everything together, so we formed input matrix here into the augmented coefficient matrix, we convert it to row echelon form, and after we've done that, we then calculate the rank of that. So that gives us another integer called augmented rank. It's from row echelon matrix dot rank, and we do it after converting to row echelon form simply because that would save having to do the row echelon calculation twice. So if you recall, the code to compute the rank of the matrix, we'll try to do it using the row echelon method first, and it would just be really inefficient to do the row echelon conversion twice in the situation that is successful. So if we convert to row echelon form first and then we compute the rank, the matrix is already in row echelon form, so computing the rank should be that much more efficient. And then all we're going to do is actually all we're going to do then is to compare those ranks with the number of rows. So we talked about this before. We have these three conditions here, exactly as we've just talked about, and we simply have if the original rank is equal to the augmented rank and the original rank is less than input matrix dot get num rows, then we know that we have a situation with no unique solution, so we return QB linsolve underscore no unique solution. Else we check if original rank is less than the augmented rank. If it is, then we know we have no solutions at all, so we return QB linsolve underscore no solutions. Otherwise, we drop into the code that we looked at before when we talked about solving systems of linear equations, and that will go through and will then calculate the output. And that's it. That's all of the changes that I've made, and I think that pretty much brings to a close really our work on solving systems of linear equations. Now I did mention that I'd made changes to QB vector as well, so let's just have a look at that. Okay, so just quickly looking at the QB vector class, the only thing that I've added is, as I said, the extra constructor here that allows us to create an instance of the class and simply specify a number of dimensions as a single integer parameter. And the reason to do that is that there are now conditions where the user will want to create a new vector, QB vector object, but they won't have any data to put into it, but they do want to specify what size it would be. I did originally think of doing this as a resize function, but then it occurred to me that actually it doesn't make any sense to ever resize a vector. There is no, that I can think of anyway, sensible situation where anyone would ever want to do that. So I think it makes a lot more sense to add a new constructor that simply allows the user to specify what size the vector should be, and it will initialize all of the elements of that vector for the specified number of dimensions to 0. So if we just quickly look, that's the constructor code, very simple. It's just here. So we simply copy numdims into m underscore ndims, and we set m underscore vector data equal to std vector of type t, numdims, and we initialize everything to 0. And of course we static cast our zeros to type t, so to make sure that we populate the vector with the right type of data. And that is all of the changes that I've made to the QB vector class. Okay, so the last thing to look at then is testing. How do we actually go about testing the new code that we've written? So I've come into the code here, which is our test code underscore qblinsolve .cpp, and this is everything else. Everything here is exactly as it should be. We have int main. So I've left all of the tests that we've talked about before in there as they were. We've got the random test for a 10 by 10 matrix. We test computation of the matrix rank. We test the situation when Gaussian elimination fails. That's what we looked at in the previous video last week. And all I've done is add some extra new code here to test the two possible conditions with no solution. So in both cases, all we do inside these scoping operators, so we don't need to worry about doubling up our variable names, we simply define our system accordingly. So a system with an infinite number of solutions or no unique solution is Yes, simply given by the A coefficient matrix of 1, 0, 0, 0, 1, 0, 1, 1, 0. Okay, so this system represents two planes, one in the x-axis, one in the y-axis, and then a diagonal plane across x and y. So these are all going to intersect along a line. This is similar to the example that we saw geometrically. And the b vector there, remember, we're working with ax equals b, I simply set 0, 0, 0. So we simply set that up into a 3 by 3 matrix there as follows, and bvec into a qb vector object, like so. And we define, this is where we use the new constructor for the vector class. We define a QB vector of type double called solution, and we just specify a single integer, so that will make it have 3 dimensions. So that is a 3-dimensional instance of QB vector called solution, where all of the elements will be initialized to 0. And we then call our QB_lin_sol function, collecting int test from it, as we do, type double. We pass amat, bvec, and solution, and that will put the answer into solution, assuming that there is a valid one. So if test is greater than 0, then we know that it's been successful. It returns, I think I said 0, but it does actually return 1 in the event of success. So we test if test is greater than 0, then we print the vector, else we print the error condition, and we print what the result of test was. And then this code is exactly the same, except we amat and bvec are defined differently. So here now we have 3 parallel planes, all in the x-axis, so 1, 0, 0, 1, 0, 0, 1, 0, 0, that gives us 3 planes, equals 0, minus 1, and 1, so they're at different heights. And very clearly that's a system that will have no solution, so we would expect to see the appropriate error code out of that. Okay, that's pretty much everything for the test code, just except to say, of course, I did change the QB_lin_solve function slightly. So whereas before we were returning the actual result, we returned a QB vector object from the QB_lin_sol function, we're no longer doing that anymore. So if we just find where the function is called, it's here. So now, of course, we return test, we return an integer, and so I've had to just go through and modify all of the test code to be compatible with that. So we simply pass amat, bvec, and test result. So notice that we don't pass references to these anymore. Previously, the QB_lin_sol function accepted these two as pointers, so we pass them as reference to amat and reference to bvec. We don't need to do that now because we're just doing pass by reference. And similarly, test result, we simply pass the blank QB vector there. So I've just gone through and modified the calls to QB_lin_solve everywhere throughout this code just to support that. Okay, right. So let's go to our terminal window. And let's just compile our code, minus g++, or g++, sorry, minus o test code underscore qb linear solve. I want to compile qb, sorry, test, compile test code underscore qb linear solve.cpp minus std equals c++17. Just compile that. And then run that / test code underscore qb linear solve. Okay, and the first thing that we see down here, these are the new test code. They're testing the 2 possible conditions with no solution. A system with an infinite number of solutions returns error condition -1, and a system with no solutions returns error condition -2. Okay, which is exactly what we wanted. And just if we look back, it's always a good idea to look back at all of these other tests, make sure everything is still working as it should. So we started from here. Conversion to row echelon form works, solving the system of equations works. An example with no unique solution, we notice that now we just get a result 0, 0, 0. The original test code I wrote for this, it doesn't do anything about interpreting the error code, so we don't get anything else, but we see that's probably more sensible than the situation we had before. We then test the random coefficient matrix, and we see that that all works, okay? And test computation of the matrix rank, a solvable system has a rank of 3, an unsolvable system there with a rank of 2, and so on. And the situation where Gaussian elimination fails, we have that as a rank of 2, and or 0 matrix gives a rank of 0, larger example gives a rank of 10, and there's 4 by 4 tests I threw in there with a rank of 2, and then of course the new test code that we have there. So there we go, that's, as I say, pretty much everything that we want to do now really for solving systems of linear equations. So we've created code that can take any system of linear equations in the form of ax equals b, we just put in a and b, and it will give us the result out, providing that we have the same number of equations and the same number of unknowns. So that's all very well and good as it is. We've also looked at how we can calculate the matrix rank. We spent 2 videos, the last video and the last but one video, looking at ways of calculating the matrix rank. And then we've seen today how we can use those results from calculating the matrix rank to tell us useful things about the system of equations, even in the situation where we can't actually find a solution. So I think the next thing that it makes sense to look at, which will be in the next video, we're going to start looking at it anyway in the next video, is how we can deal with systems of equations where we have more equations than unknowns. And that actually does crop up probably more often than you might think. And we're going to look at implementing a linear least squares approximation to the answer for that. But anyway, I think we've definitely covered enough for today, so there we go. Okay, so that's really everything I wanted to talk about today. We've had a look at how we can use the matrix rank of the coefficient matrix and the matrix rank of the augmented coefficient matrix, along with the number of rows in the original matrix, to tell us which of the two possible categories our system of equations falls into, in the case that we have a system that cannot be solved. As I said when we were at the computer looking at the code just now, the next logical thing to go on to look at, and what I want to start looking at in the next video, is how we can deal with systems of equations when we have more equations than we have unknowns, and we're going to look at doing that using linear least squares. So I hope that will be of interest. Anyway, as I said at the beginning, if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel. Anyway, listen, I hope you've enjoyed the video. It's been a great deal of pleasure making it, and I really look forward to seeing you in the next one. Thank you very much for watching. Bye.